Hello everyone, May the 4th is coming up soon, and as usual around this time, I contemplate how to implement science fiction ships in Kerbal Space Program. Not just Star Wars ones, but a lot of times it ends up being mainly Star Wars ones. And I have already implemented the X-Wing in Kerbal Space Program. It's part of my sci-fi pack. I'll link it in the video description. But in this video, I want to contemplate how exactly we might make it quote-unquote realistic. Well, we can't do anything about the hyperdrive and going between stars, but the real question is, to what extent can we turn it into something that can get off of planets, that can travel between planets relatively quickly, and do that sort of thing? Of course, with advanced technology and great efficiency, it really doesn't have much room for fuel tanks, does it? And so we need a very efficient system, and yet we still need to be able to generate a high amount of thrust because we have to get off of a planet with an atmosphere about the size of Earth, let's say. And we also need to be able to travel with good efficiency between the planets. So that means high ISP. So I have decided to do the calculations for this. And so this is going to be a math thing. I'm going to talk through exactly what can be done about this situation. Now, this is admittedly not the kind of thing that I tend to get many views on. As soon as I show this as a text document, people run away. That's why I started with Blender and the X-Wing there. But we are going to talk about a realistic X-Wing design that might work, and I'm going to go through it in detail, and then you guys can tell me what you think. So what are our requirements? Must be able to reach low Earth orbit from the ground using intake air is possible, right? It seems to have intakes, right? So we're going to assume that they are accessible, that we can make use of them. We need 9,500 meters per second of delta V at 1.5 g acceleration from the start. It also must be able to reach Mars orbit from the ground on Mars without using intake air. So that's 4,500 meters per second delta V at 0.6 g's acceleration. Must be able to travel between the inner planets without hyperdrive within 2 weeks. The maximum amount of time a person in the cockpit would be able to handle it based on the Gemini missions. The cockpit seems to be, a normal cockpit. The Gemini astronauts were able to deal with it for 2 weeks. I am going to assume that 2 weeks is possible going from one planet to another. We're not going to deal with outer planet distances. I have never actually seen in Star Wars them traveling between outer planet kind of things. They're always traveling between small rocky planets. So we're going to go with that to simplify things. Must use S-foils to dissipate heat as radiators. Well, what else are we going to use, right? Must properly shield the reactor that is used. So this is our realism. We are going to actually have some delta V calculations. We're actually going to talk about the radiators and shielding. So the assumptions, we'll use aneutronic fusion, that's proton boron 11, because anything else would be too difficult to shield. It produced too many neutrons, and then our shield thickness will be heavier than anything we want it to be. It's realistically it's probably heavier than we want it to be anyway, but we're going to assume that the people of the ancient galaxy were a little bit more radiation resilient, maybe. I don't know. But it depends on how you look at the confinement of it. And also the fact that, we are running it for at least 2 weeks, right? So let's not talk about it. Anyway, but we'll try our best. For the high thrust modes, we are using hydrogen and, when possible, intake air. For cruise, we are using the pure fusion product, so there's minimum waste on energy conversion. So we're just spitting out the result of the proton-boron fusion, okay? And so it's the actual fusion results that we are sending out there. We have advanced materials, both for construction and for radiators, graphene or something like that. So we can get a good temperature on them. So radiator heat rejection. Available area is assumed to be about 60 square meters. This is, it's a little bit of a problem because the S-foils have surfaces that face each other, right? So I'm not counting the full amount of those surfaces, but we need them to radiate a little bit. So it's sort of like each of those has got a good 12 square meters and a sort of bad a bad 3 square meters, uh, sort of like that. Anyway, that amounts to 60 square meters is what we're aiming for here with the 4 wings, if you will. And then there's the equation that determines how much heat rejection that we can get out of the radiation from the radiators, not the radiation from the reactor. So this will scale our reactor, is what I'm saying. So at 2000 Kelvin, which is pretty hot, but maybe we can manage that. We will, I mean, certainly some of the fancier radiators in KSP Interstellar can do much more than that. We will have approximately 50 megawatts heat rejection to work with based on this equation. And we are using direct thrust rather than converting to power. So most of the energy is released, so we can expect in this futuristic setting to get an efficiency of 99%. I'm saying that. I'm asserting that. I've talked about the efficiency before, and I've corrected the far future engines based on the better ones having 99%, or even with the pure antimatter one having better than 99%, but this is what we're going with, 99%, which is better than anything we can do right now, by the way, of course. So when we say realism, we mean physically possible in theory. We're not talking about like we can do it right now. Leading to a maximum reactor size of 5 gigawatts, right? If 50 megawatts is the 1% that we have to deal with as far as waste, then your reactor is 5 gigawatts. Now, note that the reactor only needs to run for maximum acceleration when taking off from Earth-like atmospheric planets. So we don't need to have the full 1.5 Gs of acceleration later on in launch. We just need it right off the ground, and then we can pull back, especially since the craft will be getting lighter as it uses the propellant, but also because you don't need to go 1.5 Gs all the way to orbit, right? So you can go to 1 G and then maybe even less than 1 G. So there will be atmospheric thermal dissipation as well. The atmosphere will help. We don't have to rely just on radiation to get rid of the thermal load. And in all other flight regimes, the reactor can run at lower power so that it doesn't approach the limits of the heat rejection system. There's a caveat to that. If we really wanted to cruise between the planets at full tilt for 2 weeks, it would be using the full capabilities of the reactor. So, well, you might need to take more than 2 weeks. But anyway, performance estimation. Since thrust equals 2 times the power divided by the exhaust velocity, saying for a 13-ton X-Wing, there's just, I seem to recall that the X-Wings were supposed to be 13 tons. Then at 1.5 Gs, we need 19.5-ton thrust. Let's just call it 20 tons of thrust. And we would get about an exhaust velocity of 50 kilometers per second. So that's an ISP of 5,000. How do you get this? Well, I mean, you can do this one in your head. 2 times the power. The power is 5 gigawatts, so that's 10 billion. 10 billion, and then the thrust that we need is 20 tons, which is about 200 kilonewtons. So that's 200,000 on the thrust side, and then here we have 10 billion. And if you move the exhaust velocity over by multiplying and then divide the thrust, it's the 10 billion divided by the thrust of 200,000, so you get 50,000 and 50,000 kilometers per second, 50,000 meters per second. Exhaust velocity is about 5,000 seconds of ISP, output seconds. Okay, dry mass estimation. We're going to assume that things are light with advanced materials, and most of this is just making up numbers, I say. Okay, so yeah. We have the primary structure, I've said, is 3.4 tons. The cockpit is 0.7 tons. The avionics is, with the astromech droid, is 300 kilograms. The weapons and capacitors for the weapons are 0.9 tons. That could be lighter, really. Landing gear, 0.3 tons. Usually, I would say the dry mass is 14 tons, maybe on with not advanced materials, it'd be like 0.42. We're going with advanced materials, so. The 5 gigawatt A neutronic fusion core we've got in at 2.4 tons. That's a very good, whatchamacallit? Oh, yeah, effective specific power. That's this effective specific power is including the magnets, the feed, and the power systems. All of that combined up here, the superconducting magnets and everything, is 5.4 tons. And then we get a specific power of basically 1 megawatt per kilogram. That's what I was aiming for. Okay, so I sort of had this predetermined. I wanted about 5 tons so that we ended up with 1 megawatt per kilogram. And of course, I'm making up these numbers right here, so that's what we're going with. 1 megawatt per kilogram is what we're going with for the 5 gigawatt reactor and its systems. So then we have the radiator panels. That's just, I just made it a ton. Additional armor, micrometeoroid skin, 400 kilograms. And then a radiation shield, 1.6 tons. That breaks down here. Mostly the tungsten for X-rays and gamma rays, because that's mainly what an aneutronic thing does. Aneutronic doesn't mean that it doesn't have neutrons, so we have some for that. Some shielding for that. And then the structural frame and thermal isolation. So, that is how the mass of it breaks down as far as I'm concerned. And now that I've made that up, I mean, we have to come up with something. I mean, how are you going to do it otherwise? So, okay. We try to, now we try to do it legitimately. Fusion reaction mass. I'm going to guess and check. We're going with guess and check here. I'm guessing that I'm going to load in 3 tons. Okay? I don't think it's got a whole lot of room for more. So we're going with 3 tons, and I'll have to double check the volume that would actually take up later. Assuming a 2-week trip, we might scale up the X-Wing just a little bit if it doesn't have enough volume. Assuming a 2-week trip with accelerating half the time and decelerating half the time, so Bakistochrone, that's 1.2 million seconds, okay? Because we have to do meters per second and all this. And I've decided that, we had up here that the requirement was it should be able to travel between the inner planets. And I've said that the range we're talking about is 200 million kilometers. Weird to talk about range when it comes to space, but in this case, when you've got a Bakistochrone situation and a limited amount of time, you then end up with range. If you don't have a limited amount of time, of course, you can just keep going whenever or however you like. So, or wherever you like. So 200 million kilometers travel distance in 1.2 million seconds means that we have to go 166.7 kilometers per second average. And that means, since we're, assuming that the acceleration is even though we're actually losing mass, and so our acceleration is going up, we're just going to assume that the acceleration is flat. And so we're going to get a peak speed of 334.4 kilometers per second. Now, if we're accelerating to that peak speed and then decelerating, so we start at 0, get to 334, then once we get to 334, we start decelerating back to 0, then that takes a total delta V of double that. So we've got that. Now, we said that this is 3 tons, so that's a 17-ton wet mass, and the dry mass is 14 tons. That means that we have an ln 17 over 14 in our mass factor in the rocket equation. So mass factor ends up being that number. So therefore, the required exhaust velocity to get the delta V is 3.4 million meters per second, or 3,444 kilometers per second. So that is an ISP of 350,000 about. Okay, I don't use that. I'm just giving a round number so that people can wrap their head around it. So I take this number and then figure out the thrust that I would get with 5 gigawatts, because we have that equation up here, this one. So get my 5 gigawatt thrust, which means that we can generate 2.9 kilonewtons of thrust. That gives us this acceleration, 0.18. So then I compare with what I would need as an acceleration, because we need this amount of delta V expended altogether, and we have this amount of time. That gives us an acceleration. That divided by the seconds is an acceleration, and that's the acceleration. Well, we don't have that acceleration, right? We have the third of that acceleration. So that's not good. Sad face. So allowing for 3 weeks, though, instead of a 2-week trip, let's say 3 weeks then. Okay, maybe our Luke Skywalker can survive that. So 3 weeks cooped up in that little cockpit with only R2-D2 to speak to. We have 111.1 kilometers per second average speed, 222.2 kilometers per second peak. So, I mean, it's just basically a straight ratio, right? We've cut down the time. I mean, we've increased time, so we cut down the speed by a flat amount, direct relation. Total delta V then is 444.4. So that's nice. Required exhaust velocity, working the same way again with the rocket equation, same mass ratio, as 2,288 kilometers per second, or an ISP of 230,000. Well, if we have that lower ISP, then we get more thrust with our 5 gigawatts, because it's a direct trade-off with that power equation. So now we get more thrust and we need lower ISP. The more thrust gives us more acceleration. We can now get 0.27. We have more time and we need less delta V. So we need only 444.4, and we're dividing that now by 1.8 million seconds. So then we get acceleration necessary of 0.247 meters per second squared, and that is less than the acceleration we need. So now we know we can do it. Therefore, we can get 200 million kilometers in 3 weeks, but we can't get the 2 weeks. So I can't do that unless we carry more propellant. But this is all assuming that we go with the 3 tons. We had written that in. That's the guess and check. So if we wanted to bump that up, we could then potentially do this. So we would have to carry a lot more propellant, though, because we're talking... We are not getting fast enough here. I don't think bumping up the propellant would help, actually. I think we would have to bump up the the reactor size. So we would need more than 5 gigawatts. We would need something more powerful. But maybe even a modest increase in the reactor size would be able to do it. Because, it changes both... well, it's a trade-off, so both thrust and the ISP can be increased by the increase in the reactor. So, anyway, but this seemed okay to me. I went with the 3 tons of propellant, 5 gigawatts. After all, we can't do more than 5 gigawatts as long as we keep the 99% efficiency on the thermal stuff. So, as long as we have the radiator size the way we do, we can't do more than 5 gigawatts, so we're going with it. So, fine, 3 weeks. Now we have to check the high thrust situation. So now, in order to travel, we need to have the 17 tons available to us. And now I, once again, guess and check, assume 2 tons of hydrogen inside. This ideally stored in the wings, potentially. Well, I don't know if it's ideally. I'll have to figure out where all this fits. But okay, let's say we've got 2 tons. So that's now 19 tons total. And if we want 0.6 Gs, which is a nice margin on Mars's gravity. Basically, I thought of Mars's gravity as 0.4 multiplied by 1.5, just like we did with Earth. That's 0.6 Gs. So then we need this amount of thrust. Okay, 111.8 kilonewtons. Not much, but it's a small fighter, right? But that means that they can only get 0.6 Gs. It's not making like fighter jet maneuvers here, but you know that they were messing around with that. Anyway, I mean, if you want to waste the fuel, you can. I mean, we could just pump more hydrogen through, and then you can boost yourself to whatever thrust you like, as long as you're willing to sacrifice the efficiency. So anyway, we'll set that aside for now, the fighter jet aspect of it. So from the 5 gigawatts of power in our reactor, we can get this exhaust velocity, or about 9,100 seconds of ISP. Not crazy, right? I mean, seems pretty tame. That's what you get if you want the thrust. If you are willing to accept lower thrust, you get more ISP. It's just like that. So it's because the reactor is putting the same energy into the little particles going out. And we're assuming a pretty perfect conversion on that because why not? But it is advanced technology. A pretty perfect conversion is fine. But let's go with that. And so we get this 9,100 seconds of ISP. Since we need 4,500 meters per second to get from Mars' surface to Mars' orbit, that means working the rocket equation backwards, we need a mass factor of 0.05. When I say mass factor, that's the ln of the wet mass over the dry mass. That whole number is 0.0503. And if we then we then use e to that number and multiply by the what is now the dry mass, the 17 tons with the cruise fuel, means that we get 17.88. So we need 0.88 tons of the hydrogen. So that's not much. I mean, it seems like we could fit that in, right? So with thrust enough to carry up to 2 tons of hydrogen, right? We assumed 2 tons of hydrogen. We can get to Mars orbit with just the 0.88 tons of hydrogen. So we will assume that we're carrying the 2 tons, and but that includes the tankage mass, and so it's actually 1.8 tons carried. And I forget about this. I forget about this down here. I say 2 tons. So really, it's probably 19.2 and or whatever the tankage mass is. I wrote that and then I totally forgot that I made that claim. Okay, no, maybe maybe the structural mass can contain the hydrogen. I don't know. We'll have to do some finer work on this if we really want to make it rigorous. I'm of course dumping the entire internals of the X-Wing as per lore because we need to actually make this all work out. So whatever lore says inside the X-Wing, I'm ignoring that by necessity. Except for the hyperdrive, we haven't. Well, yeah, I've ignored the hyperdrive. We're going to assume that the hyperdrive is massless, and possibly no. It's fine if it carries if it occupies a volume. We just can't have it any heavier than it is right now, or it can be part of the structural mass. I don't know. We haven't accounted for it. So anyway, I don't know how much a hyperdrive would weigh. Okay, so let's set that aside for now. All right. Earth requirement, that's the hard one. We need 1.5 Gs to get off of Earth, and that means for 19 tons, we're going to need 279.5 kilonewtons. Is that right? 1.5 Gs. Yeah, I guess so. Yeah, it's 2.5 times the Mars one. Okay, so from 5 gigawatts of power. Then if we get more thrust, we get less ISP. That's the new amount of exhaust velocity. And so now we have a requirement of 9,500 meters per second. That's the new mass factor. That's the ln of the wet mass versus dry mass that we need. But that leads to 22.17 tons for the hydrogen. And that means 5.17 tons of hydrogen. We don't have room for 5 tons of hydrogen. And we didn't plan for it with our thrust. If we allow this, then we are going to have to increase this and increase the thrust. And then if we increase the thrust, we lower the exhaust velocity and the ISP, and it's just like a vicious cycle at that point. So if we carry drop tanks, which would be the solution to not having enough volume, then we have to increase the thrust, decrease the ISP, and so we need the intake air. So it's good. It's good that the X-Wing had the whole being able to take in intake air potentially deal. I know that what looks like an intake is probably something else, but we're going to pretend that they're intakes. Okay, so by the time we accelerate using the intake air, we should no longer need as high as an acceleration. I'm taking advantage of that. So by the time we finish with the intake air, I'm going to say that we only need 1.2 Gs instead of 1.5. So double Mars makes the math easier. And then that means 223.6 kilonewtons. It's still based on the 19 tons, right? We didn't burn any of that. We're just taking the intake air, shoving it through the reactor, and getting our thrust. So there doesn't need to be any combustion or anything, so we don't need to use any of the fuel with that. We're just accelerating the intake air with the energy. Well, okay, we are using some from the fusion reactor. So we're using the fusion reactants, but we're not using too much of them. At the rate that we would need to release the energy to accelerate the intake air, we're not using that much, so our mass wouldn't diminish very much. So anyway, we get this exhaust velocity now, so we get to bump up our exhaust velocity because we don't need as much thrust, and that amounts to 4,500 seconds of ISP instead of 3,600. So now our maximum current delta V with 2 tons of internal hydrogen, here I did 2 tons instead of doing 1.8, 4,974 meters per second we can get out of the 2 tons once we've finished with the intake air and we need to continue on to orbit. I've assumed that we're going to have some losses, gravity losses, etc. So I'm only assuming 4,500. I don't think that's enough to make up for the fact I added that extra 2.2 tons in. Okay, so 4,500 means that from the intake air, we're going to need 3,300. We need to get to a speed of 3,300 meters per second, right? Some of it's going to be extra delta V necessary to fight against gravity or drag, but we just need to hit a speed of 3,300, about Mach 10. And there's scramjet territory, but we're not actually relying on supersonic combustion, so we don't actually need to worry about the scramjet part of it. Not that, I mean, the scramjet would be easier technology anyway, potentially. So anyway, we've got the reactor. We don't have to worry about doing supersonic combustion. And the real only problem is getting to Mach 10 when you're shaped like an X-Wing is really bad. If you're in an atmosphere, I mean. So, yeah. That's the downside. So, anyway, what we end up with here is we've got enough. We've got the parameters for realistic X-Wing, as I put here. With sufficiently advanced technology, we can make magic happen. A corollary to Arthur C. Clarke's famous law. So there you have it. That's the math of a realistic X-Wing. I will probably try to implement it with my model in Kerbal Space Program, so it'll have the math all worked out and it'll be able to give you this kind of performance, and that should be fun. But of course, we don't have the hyperdrive deal, though I forget if I ever fitted a warp drive into the X-Wing model. I probably didn't, but I have done so for the Star Trek Enterprise model I have in the sci-fi pack. Anyway, if you want to play around with the sci-fi pack, by all means. And there's a Death Star in there too, and also a Star Destroyer, so it has things. And we will continue trying to make sci-fi work, as it were. I think I now know a dangerous amount, just enough to make a mess like this, basically. So with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.